Today we'll talk about absorbers. RF absorbers are very popular in today's era. Reason being, these are used for energy harvesting, these are used for electromagnetic compatibility, these are used for scanning and imaging, these are used as sensors for measuring temperature in harsh environment, these are used as retina, these are used as load. So there are tremendous applications as stealth, because we know that B-2 bomber and there are fighter aircrafts, they can be invisible by using these absorber material on their surfaces. So for defense purpose, these RF absorbers are crucial, as well as for energy harvesting. These are very useful. Now, for they are generally made up from graphite, graphene, silicon, ceramic foam, urethane, FR4, elastomers. So there are various materials available to design these RF absorbers. Now, as we know, there is a spectrum at RF frequencies, and depending on the spectrum, we choose the materials to design these RF absorbers. Now, there are various parameters while we design and test these RF absorbers for characterizing and synthesizing. These are, we generally drive absorptance, that is known as absorption in percentage. We work out to match free space impedance, that is 377 ohm. By using quarter wave transformers, we try to match Zin, Z0, ZL. Then at what frequency, because these absorbers are designed for resonant frequency, so we try to get S11, that is reflection coefficient parameter. We try to get S21, that is forward power, or you can say transfer power. Then we try to measure the permittivity. Permittivity can be split into two parts. One is imaginary part and second is real part. Similarly, we measure relative permeability, that is real part of permeability and imaginary part of the permeability. We try to develop these absorbers as a polarization independent, or in other way we can say that as incidence angle must be measured at different theta values, that is 10 degree, 20 degree, 30 degree, 40 degree, 50 degree. So wide angle response is better in case of absorptance. Then we try to compute A oblique M, that is surface magnetic current. Then V upon M, that is E field, or we can say the capacitance, as well as the capacitance is developed from permittivity, and the inductance is developed from permeability. So we want to increase the imaginary part so that absorptance is better. Then there are three crucial parameters which we need to work out in the design part, that is Zin, Z0 and ZL. It is very difficult task to match the impedance of total absorber with the free space impedance, and that is our critical requirement also. Then there are SRR. These SRR are split ring resolators. These are selective, and we try to develop these SRR on the surface. There are various type of SRRs available: T, H, ring, split ring resolators, then square, rectangular. So there are different shape of SRR which we use in selective surface to receive for a particular wavelength on the substrate. Then we try to compute equivalent RLC circuit of the absorber, and there are few formulations which we use during the design of SRR. One is A is equal to 1 minus S11 square minus S21 square, that is absorptance. Then the second is Z is equal to 1 plus S11 upon 1 minus S11. So we developed one SRR. I'll show you the structure that for developing that absorber, we have taken the bottom layer as gold. Then on that gold part, we have placed silicon layer. Then on the silicon layer, we have used SiO2 substrate, and on top of SiO2 substrate, we have used SRR of gold. And then in the anechoic chamber, we can see how much absorption is being obtained. So reflection and forward power, these both things are being measured in the anechoic chamber. Thank you. This much is sufficient for today's class.